Well, hi there, boys and girls. Today we're going to talk about two theorems. One is Rolles Theorem, and the other one is the mean value theorem. So let's go ahead and get started with this. Rolles Theorem says that if you've got a function that's continuous on a closed interval and differentiable on the open interval, and of course we know that we don't take derivatives at endpoints anyway, and you have a third requirement, and that's that y values are equal at some point. And then there is a number c in between a and b such that f prime of c equals 0. This says that f has to have a critical point in this interval. And so this is like the what goes up must come down theorem. If you have two equivalent y values, so there's a and there's b, and we have that f of a is equal to f of b. So what this is saying is there's no way for you to connect these two dots without making the derivative 0 somewhere in here, as long as you're drawing a differentiable graph. So like what goes up must come down. Somewhere in there, you made a spot that was flat where the derivative was 0. Not real shocking. It's pretty self-explanatory, and I call this like, the only reason this is really important is Rolle's theorem is used to prove the mean value theorem, but other than that, it's pretty much a common sense theorem. Now let's take a look at the second one, which is used much more often. It has a lot more to say. Here we've got a continuous function and a differentiable function, but now we're going to say that there's a number c such that this equation here is true. That's one form of it. I want to remind you that on the right hand side, this is called the average rate of change formula. That's also the slope of the secant line. So the average rate of change has to be equal to the derivative somewhere. Now you can rewrite this by multiplying both sides by b minus a and get it in this form as well, which is the beginnings of our Taylor polynomials we'll do in the spring. So let's go ahead and look at this geometrically. The tangent line slope, of course, is f prime. The secant line slope, the slope of this line, is f of b minus f of a over b minus a. What the mean value theorem says is that the tangent line and the secant line have to be parallel at least one place in the interval from a to b. Let's go look at an example. And this is one of those weird examples like, oh my gosh, how am I supposed to do this? But we're going to use the mean value theorem to do this question. So we know f is continuous and differentiable on the interval from 6 to 15. And let's suppose that we know that f of 6 equals negative 2, and we know the derivative is always smaller than or equal to 10. What's the largest possible value for f of 15? What we're trying to find out here is f of 6 is negative 2. And so if we scoot on down the road here at 15, how tall can that get if we know the derivative is always less than or equal to 10? Well, I'm going to come back to this one formula right here that I circled, and I'm going to use that one right there. This tells you the difference between y coordinates, and it has to do with the slope. So I know that f of b minus f of a over b minus a is the slope of this secant line right here, but I'm going to do it in this other form. I'm going to write that f of b minus f of a has to equal f prime at some point in the interval times b minus a. So that's that second form of that equation. Now c is some point between 6 and 15, and what we're going to assume here is, let's just assume worst case scenario. Since we're trying to maximize f of 15, let's say that f prime was always 10. That's as big as it could be. So we can have that f of 15 minus f of a, or f of 6, I apologize, where b is 15 and a is 6, must equal 10 times b minus a. So f of 15 plus 2 equals 90. Subtract 2 from both sides, and so worst case scenario, it could have gone all the way up to 88, which would be way up there. But that's my own little scale, so I'll call that 88. So it's up here. All right, let's take a look at a more traditional Rolle's theorem question. Show that this function satisfies Rolle's theorem on 3 to 7 and find the corresponding values of c that the theorem guarantees. So what I'm going to have is, I'm going to graph this. It's not going to be too hard to graph that. That factors into x minus 7 times x minus 3, And so at 3 and at 7, we have roots. And it's a quadratic. You know what a quadratic looks like. And we've got a y-intercept of 21. So it's this little whoa, sorry. Let's erase that. Try that again. Up here at 21 is our y-intercept. And so we know quadratics just come down here like this. I don't know how low it goes. We'll answer that in a few days, though. We'll find maximums and minimums. So it looks something like this. So from 3 to 7 is the function continuous. Well, yes, it's continuous because we know that all polynomials are continuous everywhere. Is it differentiable? Yes, there are no sharp turns and no vertical tangent lines. Differentiable. My handwriting's not very good today. Is it very well? Very good? I don't know. My handwriting's not well. Whatever. Okay, now what about the points 3 and 7? What is f of 7? Well, f of 7 and f of 3 are both equal to the same thing. So that means that between 3 and 7, we must have a point that's critical, or where f prime equals 0. So what we're going to do is find f prime of x, which is 2x minus 10. And then we're going to set this equal to 0. And that obviously happens when x equals 5. So here at the point 5, we have a place where f prime equals 0. And 5 is in between 3 and 7. All right, let's go take a look at one more example for mean value theorem. And then I've got a question to leave you with. Here it says, given a function, find all c in the interval from 2 to 7 such that f prime of c is equal to, this is a mean value theorem question. Average rate of change equals the derivative. So here we go. This function, is it defined everywhere from 2 to 7? Well, it's undefined at 0, but after that, there's no, it's going to be continuous and differentiable. So the first thing I'm going to do is I'm going to find the average rate of change. What is this? So if you plug in 7 in for x, you're going to get 9 minus 14 over 7. Let me just go ahead and write that down. 9 minus 14 over 7. That's f of 7. Minus f of 2, which is 9 minus 14 over 2. And this is all over 5. So let's see, that's going to be 9 minus 2, which is 7. And then 9 minus 7, which is 2, over 5, and we get 1. That means that if we were to connect these two dots from 2 to 7 on this graph, it has an average slope of just going up 1. So the slope of the secant line is 1. What we have to do now is find the place where the derivative is equal to 1. So let's find f prime of x. So f prime of x, if we think about this, is 9 minus 14 x to the negative 1. F prime of x is going to be 14 over x squared. That's the derivative. So what we want to know now is when or what x value will make the derivative equal to 1. So we take 14 over x squared and set it equal to 1. So 14 must equal x squared. So x is plus or minus the square root of 14. Now the mean value theorem says this number has to be in this interval from 2 to 7. So I'm only going to use the number, the square root of 14, because negative square root of 14 is not in the interval from 2 to 7. So this answer is C. That is the place on the x-axis where the tangent line would be parallel to the secant line. Now I'm going to leave you with one last question, something to think about. Whenever I went to college, we had toll roads, and on these toll roads, we would get a little stamped ticket. Let me draw you a picture. A little stamped ticket, and you would have the time that I entered on that stamped ticket. And then when my little car would pull up to the little toll booth, there was this person inside the little toll booth that wanted my money. But sometimes there was a police officer sitting inside this toll booth, and what that police officer would do is they would look at my time stamped little ticket, and they would see how long I had been on that toll road, and then that police officer may or may not write me a ticket for speeding. So my question to you is, which one of these two theorems is he applying or she applying, and do you think they have the right to do that? Does that satisfy all the hypothesis of the theorem that you're going to tell me about? So I just want you to think about that. Did the police officer have the right to write tickets if they knew how long it took you to travel on that toll road? Just curious. Anyway, I will see you guys tomorrow.